Welcome to the video for the 17th through 19th questions on the example exam. In this one, we'll go through finding the shear stress at this point, finding the first moment of area for this point, finding the second moment of inertia for this simple cross-section, and finding the maximum stress, shear stress. Next, we have this cross-section right here, and it is subject to a shear. We want to know about the stress at this point. So, first we need to determine Q, the first moment area that deals with this. Now remember, when we're looking at a cross-section, the shear flow looks, well, it's not used right for that. The shear flow looks like this. So when we're looking at this point right here, the area that we're considering for our first moment of area is going to be this one. All of that. So for this area, Q is going to be, well, the area, and the area in this case is going to be 3.75 inches times the thickness of 0.5 inches times the lever arm from the centroid of this to the centroid of the total shape. So that is going to be equal to 9.75. Let's start this on a new line. Minus the distance from the bottom up to where we said the neutral axis was. We said that was at 7.036 inches, which leads to our first moment of area being 5.09 inches cubed for that right there. The shear stress is equal to the shear force applied times Q, the moment area, divided by our second moment of inertia, and T, our thickness. So we've got Q, we've got T, that's just going to be 1/2 of an inch. V is given as 120 kips. So we're going to next need the second moment of inertia, I. Fortunately, we've already got the neutral axis, so this should go down real smooth, real easy. So for this, remember that for rectangles, it's 1/12 base times height cubed, and we also have the parallel axis theorem, which a d squared. So the way that I would do this one is I would either break this up into two rectangles, or I'd consider the full large rectangle and subtract out the smaller rectangle represented by these two portions. Let's break it into two rectangles right there. That's going to give us well, start with this top one. We've got 1/12, the base is 8 inches. The height is 0.5 inches. Cube that. Plus, the area of this is going to be 40 square inches. That's what 4 square inches. Times the distance from the centroid of it to that is, we already determined what that is, it's 9.75 inches minus 7.036 inches. Square that, plus, new line, this will deal with the stem, which will have 1/12. The base here is 0.5 inches. The height is substantially more, 9.5 inches. Cube that, plus the area. The area is going to be 1/2 of 9.5. It's going to be 4.75 square inches times the distance to the centroid is going to be 7.036 inches minus 1/2 of 9.5 is 4.75 inches. Square that. All of that's going to give us 85.2 inches to the fourth. And now we can use this equation right here, which gives us that the shear stress at A, at that point, I guess, if I named it A, is equal to 120 kips times 5.09 inches cubed divided by 0.5 inches and 85.2 inches, and that's going to give us 5.28 KSI. All right, now let's determine what the maximum shear stress is. Now the maximum shear stress is it's going to be at the centroid, or the neutral axis. But we already found where that was. And it was 7.04 inches up. So when we're looking at this cross-section, we could, absolutely, it would be completely valid there's our neutral axis at 7 point, we could look at this area. And we would break it into two rectangles. This one up here, and then this little one right there. But that sounds like a lot more work than we need to do, because we can also look at this blue area down here. And if we do that, calculating Q becomes a lot easier. We can do that by saying that the area is going to be this 1/2 inch right here times this height, which just happens to be where we said the neutral axis was, right? 7.04 inches times the lever arm, which is just going to be from the centroid of this shape to this point, is just going to be 1/2 of 7.04. And that's going to be 12.38 inches cubed. All right, so we've got that, and we can again we can again use our equation for shear stress. It's V Q over I T. In this case, it's going to be 120 kips times 12.38 inches cubed divided by, what did I say that was? 85.2 inches to the fourth, and still 1/2 inch in thickness. And that is going to give us 34.8 KSI, which will be the maximum shear stress this section experiences from the shear.